So we have already analyzed two different approximations for the exchange and correlation energy. We do have the local density approximation, and we have also seen the generalized gradient approximation, which somehow it's based on the local density approximation, where besides the density, it also includes a correction associated to the gradient of the density. So in principle, you'd think that this GGA should work better than the LDA, but how better it is? So here we're going to summarize the performance of the GGA, the practical performance of the GGA, in order to analyze different properties of different systems versus the performance of the LDA. And I think the key feature of the improvement of the GGA with respect to the LDA, it's included here in this square here. In this the square in the text of this square here. So within the GGA, the typical error we have for the exchange energy is around 0.5 electron volts, and for the correlation energy, it's around 5% larger. Actually, correlation energy, the value of the correlation energy is usually much smaller than the value of the exchange energy. However, do you remember which were the errors that we're making within the LDA? They were much bigger. Actually, the error within the LDA for the exchange energy was around 10%. And the error for the correlation energy was around 100%. So as you can see, there's a huge difference. Actually, what happened within the LDA was a cancellation between the two, what made the LDA to work in such different systems. Here, the errors that we are making is much smaller. So even though that cancellation doesn't happen, we expect that the results that we're getting with this GGA should be much better. But how better? So in order to analyze the performance, we are going to characterize the performance when analyzing different properties. First, of course, they are just like a summary of the behavior of the performance of the GGA and LDA for different systems. It's like making an average of the performance of these functionals. So, first, let's consider what's the performance in order to analyze the cohesive energies of solids. Within the GGA, the error for the cohesive energies is 4%, which approximate might be around 0.3, 0.4 electron volts, which is not so bad. It's a very good approximation. It's a very good, a very reasonable error, especially if you remember the error that we were making within the LDA, which was much bigger, which huge. It's what was around 15% and a value of around 0.3 electron volts. So the improvement within the GGA in order to analyze the cohesive energies is big. What about the bond lengths, the unit cells, and what about that in order to analyze the geometry of the molecules and the solids? So here, the bond lengths you are getting within the GGA are around 2% larger, while within the LDA they were 2-3% shorter. So here we have to remember that within LDA we had this overbinding, or here we have just the opposite. So here the bonds are getting larger, while within the LDA they were shorter. So here there is not a big improvement, the one we are making with the GGA in order to characterize the geometry of the solid or geometry of the molecules. However, it's there within the GGA we have an improved description in general of structural properties of the solids. The transition pressures that you are getting, for example, when you have an structural transition under temperature, under pressure, it's better described usually within the GGA than within the LDA. In the same way that we are getting much better cohesive energies, here the activation energy barriers that for chemical reactions you are getting within the GGA is around 30% too low. If you remember, within the LDA it was 100% too low. So here the improvement we are getting in order to analyze that property, it's very important, which make it reasonable to use in order to analyze the chemical reactions, while within the LDA, the results that we're getting were completely unreliable for that. Besides that, within the GGA, you have a better description of the magnetic properties. For example, you know that iron, the stable structure of iron is BCC and it's ferromagnetic. And this is actually the one you are getting within the GGA. However, the minimum and the structure with the minimum energy for within the LDA is not this one. It's the FCC, the paramagnetic FCC. And that's because the LDA is not including magnetic properties in the proper way. Not in all the systems, but in many systems, as for example here in iron. Usually the magnetic properties are better described within the GGA. Besides that, the GGA makes a better description of a weak bonding. For example, hydrogen bonds are better described within the GGA than within the LDA. Additionally, the electron affinities are better described within the GGA. Actually, the error you can have for the electron affinities within the GGA is around 10%. And actually, within the GGA, you are able to have stable negative ions, while these negative ions are stable within the LDA. So LDA is not able to describe these negative ions. However, they are stable, they can be described within the GGA. However, it's also important to have in mind that the GGA favors lower coordination. Why? Because it's actually favoring the larger gradients. So when some atom has a lower coordination, somehow you have that it has lower number of bonds. So the density is more concentrated here in the bonds, so that the gradients is going to be higher when the coordination is smaller, because otherwise when you are increasing the coordination, somehow the density is going to spread more uniformly around the atom. And the GGA is favoring to have these larger gradients. Somehow it's favoring, therefore, to have a lower coordination. That's important in order to have in mind when you are analyzing some structure. And you can see that both different coordinations have very similar structures. You have similar energies. You can think that probably the one having higher coordination could be more favored, considering the more accurate functional for the exchange and correlation energies. However, additionally, the one particle energies, so the band structure you are getting within the GGA and the ones you are getting within the LDA are very similar, and actually they are very comparable to the experimental one in the for many systems. However, it's also important to have in mind that the same way as it happens in the LDA, that they were not described properly the band gaps for semiconductors and for insulators, it's also the case of the GGA. GGA does not describe properly the band gaps as well. And finally, it's important to have in mind that the van der Waals forces are not included in the GGA. So this GGA approximation does not describe properly the van der Waals forces. Neither the LDA. LDA didn't describe them as well. So if you want to analyze the interaction between, for example, rare gas atoms, where the interaction between them are basically based on these van der Waals forces, so they will not be properly described because they are not included in the GGA or in the LDA approximation. And also always not included here in the same way that LDA was not a good approximation in order to describe these strongly correlated systems where basically the correlation energy, the correlation between the electrons, were the main feature in order to describe the properties. The same happens with the GGA, which basically is a slight improvement of the LDA. So you don't expect that strongly correlated electrons are going to be well described within the GGA as well. Okay, here basically what we have done is we have summarized the performance of the GGA versus the LDA. As you can see, we expect in the beginning, the GGA improves, it's getting better performance for many properties, and for other properties getting approximately the same. So it makes that the difference in order to describe many features of the systems are not so big, but actually the performance is better for the GGA than for the LDA. But actually, for many systems, both approximations are quite often used to describe the properties of the systems, because the GGA does not make the LDA completely unreliable, even though for many features it's slightly better.